Hi everyone. Today I will walk through a Mirage project, which is a tensor program LM macro superoptimizer. The goal is to show how the repo is organized, how the compiler pipeline works, and how Mirage compiles the entire LM serving pipeline into a single persistent kernel. So I will use this high-level design doc as a map while we tour the code base. And along the way, I will highlight a few tables that AI helped me generate to clarify the architecture. So firstly, we will go through the just like an overview, which is the mental modes and architecture diagram. So first a quick mental diagram from the architecture diagram. Mirage is layered in four main parts. The first part is user APIs and front ends. Python entry points are in Python.mirage demo, which is the demo, and the benchmark. So this is where we build graphs called like search and compile and drive LLM surfing. So then we have like compiler and search engine, C++ and Rust code under source.search, source transpiler, and source transpiler. This layer searches over equivalent programs, formally verifies them, and decides layouts, styling, and fusion. And then we will have like kernel and runtime core, which is inside source kernel, so swap blocks, plus some, yep, and this just defines the tensor IRs, operators, memory management, and runtime that actually launches the kernels. And finally, we have like the recent work, which is the persistent kernel runtime (MPK). This is secret sauce for LM serving. Um, it's inside like Python Mirage, persistence kernel, and some test on the test runtime Python. This is what we compile the entire deco loop into one device side method. Um, so we can start with some entry point, which is the Python package and import is here. So basically, in practice, everything starts with import Mirage as semi. And look at that. So basically, for the library Bootstrap, then you need Python preloads three things: Z3 and two Rust spec and share libraries, which is these two. So those powerful symbolic reasoning and for more verification. Then it re-exports the main abstractions, kernel and swap block, graph APIs, CSON core bindings that talks to C++, and persistence kernel for macrokernels, and some helpers like global config and global dataset. So the Python package is seen by powerful shell. It looks like a normal DL library, but everything you do here actually feeds into like a multi-level compiler stack underneath. Um, for example, we can go to like the graph abstractions, kernels, thread block, and persistent graphs. We can see from this one, this is the where the core abstractions are happening. So kernel graph is what to compute. What it does is it will wraps a KNG graph, uh, KNG graph here, and which is a high-level tensor program graph. It will contains like math multiplication, a lot of things, element-wise operations, reductions, IM storms. So this is roughly at the PyTorch graph level, but tailored just for compilation. And we also have here the strap block.py. This is how to compute per strap block. So strap block wraps also a CY. It wraps like it's not a KNG graph. It wraps a PPG graph, which is a high-level tensor program graph. So basically, like you see all the CLUs, MapMouse, um, XV, we just describes how a kernel runs at the strap block level. All the tiling, shared memory tensors, TP level operations. Think of it as a schedule graph for a single CTA rather than the whole kernel. So we can then look at the persistent kernel.py. So this is the LLM surfing graph, which is a high-level abstraction specific for LLM inference. It lets you basically like register meta tensors like staffs and tokens and define some like fused tasks, such as like RM's norm layer, and attention blocks, and MOE blocks. You then call like compile at the end to just turn the whole decode pipeline into a single CUDA mega kernel. Uh, Actually, what I found cool is that like the persistent kernel here isn't totally like a separate system. It's just builds a bigger graph on top of the same IRs and compiler stack Mirage uses for normal tensor programs. So basically, all the improvements in the core compiler actually benefits both classic kernels and mega kernel paths. So let me take you with like a code tool from graphs to search and to transpiler and runtime. So let's first see the search and verification part, which is inside source and source.search. So once we have a graph, Mirage doesn't just lower it directly. It first runs a super optimizer search in this folder. So the first one it wants to do is like symbolic IR. So under symbolic graphs, you will see some um, symbolic tensors and operations, right? Those encode algebraic structures and constraints instead of concrete arrays. You then will have like some search engines, files like uh, search files like search.cc, search.cc, search contacts dot cc here and order.cc here. They implement the search loop. What they propose is like rewrites, alternative tellings. You can see they're trying here, and fusion patterns, also schedule orders. So there's after this we are going to like the correctness reasoning, which is the uh, range propagation, and basically this tracks the index ranges. And there's also abstract expression, plus the Rust library we just saw in the Python init to perform abstract expression analysis. Then we goes to the verification together with like the other library from the Rust backend, which is the library formal verify.so does form and probabilistic equivalence checking. This isn't just like a heuristic fusion. This is basically like tries to prove that its optimized kernel is the mathematically equivalent to the original graph. Using Z3 and Rust verification creates a safety net. Uh, I have like a table here from my doc, which basically summarizes this layer as a table. Like for example, each sub dictionary, like the symbolic graph, range propagation verification. I wrote this row in the search pipeline. The table really helps me like track what lives here. So and the next one what we need to do is the transpiler and the lowering. So we open the transpiler folder here. Once a candidate implementation is chosen and verified, the transpiler in here will turn into like concrete CUDA or Triton kernels. So for the memory planner, we have like plan dtensor memory.cc and plan stensor memory.cc. Those just decides how global and shared memory are laid out for all the tensors. Sounds kind of like cute library. There's also layout and math resolution, which is inside the resolve tensor layout, resolve tensor layout.cc, and resolve dtensor uh, beta. This just fixes the actual strides and layout metadata, so you can just like quickly glance it. It's not that important. There's the next one is like the thread block fusion and scheduling, which is resolve tb fusion.cc groups operation into tensor groups operation into thread block units. And there's also scatTB graph.cc plus plan TB swizzle.cc build TB graphs and assign architectural specific swizzles for Hopper and Blackwell. Because for example, like swizzling performs differently on Blackwell since it has like tensor memory swizzle. And finally, we can talk about its backend, like files like transpiler tb.cc. They just like target CUDA, and some like there's also Triton transpiler targets Triton, and source Nikki transpiler. This one just leverage Nikki and TMA like features on newer GPUs. So after this, we can go to like runtime and operators, which is inside like the source kernels and source thread blocks. We can see like inside this, we have like operator implementations, like reduce, right, and matrix location, just some CUDA kernels. Um, Plus runtime.cc and textregister.cc, we can write them into like runtime APIs. And there's the thread block level operations is here, like elements on array and input executor. And those are just like what transpiler uses to assemble for complex fuse kernels. And also there's, of course, there's some inside the include the mirage here. It actually exposed like a public C++ API you can see from here, which is on under like the CSUN bindings and in CPP examples. So that's probably the architecture and some like how the pipeline flow goes. We can now go to like a demo, a code example, with like how a Mac kernel is built. We use like our recent um, demo as an example. First, we will like initiate the persistent kernel. We can see from here, mpk equals to mi.persistent kernel, which sets up the multi-GPU world and the registers all the metadata tensors that will drive the decode loop entirely on device. And we'll then like define the task graph. We can see from, we can take like also the RMS norm linear, uh, oh, linear as an example. You can see like, basically like each of these calls as what we call like persistence task graph. We can, for example, here is attach. We can see we can attach inputs and other things to the graph, ties them to concrete tensors and grid block sizes, and encodes the dependency between them. Finally, after all the like you see like all the operations are ties to the graph, we can compile it into kernel. So this is where the whole pipeline we just saw kicks in. The Python graph is converted into kernels and thread block graphs. The search engine enumerates and verifies candidate implementations. The transpiler plans memory layout and TP fusion, and we end up with a single persistent CUDA kernel that encodes the entire decode loop plus the device size scheduler. So basically, what it compiles to like the traditional frameworks is really surprising. There's no per token host scheduling and no per layer kernel launch overhead. That's what compiling the surfing pipeline into device side means in concrete terms. There's some interesting discovery I have when I like look through all the repo. I like how Mirage uses like consistent graph abstractions as kernel, thread block, and persistent kernel levels. I think they'll have the same idea from Colors. It's not just three disjoint system. It's one or stack with multiple front ends. And how like we see the search and or formal verification in the Servium compiler do is really rare to see like a serving oriented compiler do heavy symbolic and search and D3 backend verification. That's strong story for both performance and correctness. And finally, I think the MPK is more like a GPU engine that other serving frameworks could plug into. It doesn't try to be like full HTTP or queuing system. It focuses on compiling the GPU side as aggressive as possible. So basically, to summarize, we start with some like um, Python graphs and pass it through symbolic search and verification, lower into CUDA and Triton kernels, and finally execute through runtime and persistent kernel macro. The high level table I showed are all derived from this repo analysis and serve as a roadmap when you dive into the code yourself. So yeah, thanks for listening and happy to dig deeper into N layer from symbolic search to MPK runtime if there are any questions or I have any chance in the future.